Hello everyone. Today we study basics of group theory. First of all, we start with some basic terms related to group like binary operation and algebraic structure. So, what is binary operation? Let G be a non-empty set if asterisk from G cross G to G, where G cross G is defined as ordered pair of elements. When AB belongs to G, then ordered pair of AB. Asterisk from G cross G to G is a mapping which shows that the elements of G cross G, that is ordered pair of AB, is mapped with asterisk, then it gives A asterisk B, which is an element of G. So asterisk is called binary operation. The image of the ordered pair AB under the function asterisk is denoted by A asterisk B. Next, we discuss an algebraic structure. Any non-empty set is equipped with one or more binary operation, then is called an algebraic structure. If set G is equipped with binary operation asterisk, then G asterisk is an algebraic structure. For example, n plus, I plus, etc., where n is the set of natural number which is equipped with binary operation addition. Similarly, set of integers equipped with binary operation addition and so on. Now, we move on to our topic, that is group. So, here question arises, what is group? Algebraic structure G asterisk, where G is non-empty set and asterisk is a binary operation, is said to be a group if it satisfies the four basic properties. The properties are: first property is called closure axiom. We understand this with the help of diagram. Closure property says that any two arbitrary elements A, say A and B, exist in G, then their resultant, that means A asterisk B, which is also an element of G. That means A belongs to G, B belongs to G implies that A asterisk B belongs to G. We also say that set is closed if closure property is satisfied. Second property is associative or associativity. Asterisk is said to be associative if any three arbitrary elements, say A, B, C, exist in G, then if it satisfies the condition A asterisk B asterisk C is equals to A asterisk B asterisk C for all A, B, C belongs to G. This property indicates that it doesn't matter the order in which operations are performed. Third is existence of identity. The set G must have a unique element, say E, such that when it is operated with any element A, it gives the same result back. That means E asterisk A is equals to A asterisk E, which is equals to A for all A belongs to G. Then this E is said to be an identity element. For example, we know that 0. If we add 0 in any number, 5 plus 0, which is also gives the same result back. So, 0 is the additive identity. Similarly, 1. If we multiply 1 with any number, then it gives the same result back. So, 1 is the multiplicative identity. Now, the last property is inverse property. Inverse property says any arbitrary element A in G, there must exist its inverse element, say A inverse, which is also comes in G, such that when A and A inverse are operated each other, it always gives an identity element E. That means A asterisk A inverse is equals to A inverse operated with A is equals to identity. So, what is group? Group is a set G with an operation asterisk and satisfy 4 basic properties: closure, associative, identity, and inverse. Now, there are 2 types of groups: abelian group and non-abelian group. Abelian group. A group is said to be abelian if it also satisfies commutative property. So, there is again question arises, what is commutative property? Commutative property is for any 2 arbitrary elements, say A and B, in set G, if A asterisk B gives the same answer as B asterisk A, for all AB belongs to G, then is said to be commutative. If all the 5 properties, closure, associative, identity, inverse, and commutative is satisfied, then the group is called an abelian group. Now, we will take an example of abelian group. This set of integer, we have to prove that the set of integer I is an abelian group with respect to addition. So, here given that I is the set of integer with additive binary operation. Now, we have to prove that the algebraic structure I plus is an abelian group. So, we have to prove the following axioms. Then first axiom is closure axiom. We know that the sum of 2 integers is also an integer. We can understand this with the help of numbers. So, the set of integer is -3, -2, -1, 0, 1, 2, 3 and so on. That means collection of negative number, positive number including 0. Now, we have to prove the following axiom. First axiom is closure axiom. Closure axiom indicate that A belongs to I, B belongs to I implies that A plus B also belongs to I. So, we take numbers, let A is equals to 5, which is an element of I. B is equals to -2, which is also belongs to I. Then we have to show that A plus B, 5 plus -2, which is equals to 3. Again, it is an element of set of integer. So, the closure axiom is satisfied. Now, the next is associative axiom. Associativity, we know that addition of integer obeys the associative axiom. Again, we take ABC. Let A is equals to 5, B is equals to -2, C is equals to 6. Then we have to prove that A plus B plus C gives the same answer as A plus B plus C. So, we find that A plus B plus C, 5 plus -2 plus 6, which is equal to 3 plus 6, that means 9. Now, next A plus B plus C. So, 5 plus -2 plus 6, which is equal to 5 plus 4, again which is equal to 9. Then it shows that the answer A plus B plus C gives the same answer as A plus B plus C. So, set of integer is satisfy the associative axiom. Now, the third axiom is identity. Let A is equals to 5, which is an element of set of integer. Then there exists 0 belongs to I, such that 5 plus 0 always gives the same answer back, that means 5, and 0 plus 5 also gives the 5. So it indicates that 0 is the additive identity. Then next is existence of inverse. Existence of inverse. Again, let for each a belongs to I, there exists minus a belongs to I such that a plus minus a is equals to 0. So let a is equals to 5. Then there exists minus 5 belongs to I such that 5 plus minus 5 gives 0. That means identity element. So minus 5 is the inverse of 5. Now the next is commutative. Commutative axiom. We know that addition of integer obeys the commutative law. That means a plus b is equals to b plus a. So we find that a plus b and b plus a. Let a is equals to 5, b is equals to minus 2. Then a plus b, 5 plus minus 2 is equals to 3, and b plus a, minus 2 plus 5 is equals to 3. Again, a plus b gives the same answer as b plus a. So commutative axiom is also satisfied. Hence, set algebraic structure I plus, that means set of integer with the additive binary operation, satisfies the following axiom: closure, associative, identity, inverse, and commutative. Hence, I plus is an abelian group. If commutative axiom is not satisfied, then the group is called non-abelian group. At last, we discuss some definitions with the help of flowchart. If only closure axiom is satisfied, then the algebraic structure is called groupoid. If two axioms, closure and associative, are satisfied, then an algebraic structure is called semi-group. If three axioms, closure, associativity and existence of identity, are satisfied, then an algebraic structure is called monoid. If four conditions, closure, associative, existence of identity, existence of inverse, are satisfied, then an algebraic structure is called group. If all the five axioms, closure, associative, existence of identity, existence of inverse and commutative axioms are satisfied, then an algebraic structure is called an abelian group. Thank you.